Okay, if we don't have more questions, I think we can move to the next session, which is going to be with Dr. Taha Selim uh, um, to talk to us about quantum computing for chemistry. It's an extension of part of what we talked about today, but maybe get deep into the field to talk to us about quantum computing for chemistry in specific.
Yeah,
By the way,
thanks, Dr.
Dr. Taha Selim's PhD is actually in quantum chemistry. So you are getting the word from the highest expert.
Yeah, thanks, Dr. Ahmed, very much for the nice words indeed and a nice endorsement. So today we are gonna highlight the quantum chemistry. Of course, it's a very big field, but we just the main goal is to highlight why we do need quantum computing for chemistry, what are the main challenges, and how we can do a simple algorithm. Tomorrow, you are going to see a use case presented by Alan Chansey about using one of the advanced algorithms that Ahmed Selim has mentioned earlier, the sample-based quantum diagonalization. However, today we are going to talk about the basics and the foundation. So I'm going to share my slides now. Course, the data was not updated. I tried to update my LaTeX code, but apparently one of the libraries I use for drawing wasn't updated, so I couldn't render. So I recovered an old version of the PDF. So that's worked out in the last 15 minutes, luckily. So that was great indeed. Okay, so now why do we need the ground state of a given molecular system? So we have spoke earlier earlier in the panel discussion that the ground state expresses the energy required to keep the molecular structure at equilibrium. So the equilibrium position or the default structure, or to keep the molecule at a certain structure, we need some sort of a binding energy, and indeed the ground state energy is sort of the default state energy, like we have the ground state energy of hydrogen molecule, of carbon dioxide, and so on. Since we can safely say that in the harmonic approximation, we can decouple the molecular motion into 3 degrees of freedom. We can say we have vibrational motion, we can have translational motion, and of course, electronic transitional motion. If we talk about the simplest one, this is one of the use cases I worked on during my PhD about carbon dioxide. We are going to talk about it later on in the last panel when we talk about the bulk of quantum chemistry and computing for the curious. If you see about the carbon dioxide, we have for the vibration, we have 4 vibrational modes. So we have the rotation. Indeed, this is the overall rotation of the molecule. We can have electrons that can make a transition, and we have vibrational modes. And if we go to the vibrational modes, we have about 4 vibrational modes. 2 of them are degenerate because the molecule is linear, so it can bend in the plane and out of the plane, and this can result in an overall rotation. So that's called the vibrational angular momentum. Away from this complicated stuff, what we care in spectroscopy is how to measure the correct spectra of the molecule in high resolution indeed, and to know the specific transitions that can happen. And indeed, the energy spectra would contain the ground state energy, which has the default equilibrium structure of the molecule. Now we see an example. Molecular vibrations are important in understanding the molecular structure because they expresses the nuclear motion. So if we have a diatomic molecule like carbon monoxide or CO, the molecule at the equilibrium have what's called equilibrium bond length Re. So this is balanced or the default structure, and the molecule can stretch. So So the bond can stretch, and hence we have stretching, and of course the bond can compress, and we have sort of contraction of the molecule, and together this stretching and the compression would give us what we know about the vibrational motion. During this, we get what we call the potential energy surface, and then if the molecule is completely, the bond length is very small, the 2 atoms get close to one another, and we have the repulsive wall. This is why we have very huge repulsive wall. This is called the van der Waals wall. And then at the equilibrium structure, this is the default structure. We have the lowest energy, and this is typically in negative if the molecule is bounded. And then we continue until we achieve what we call the dissociation energy, and it means that the bond has stretched to the limit that the two atoms can no longer back to one another naturally, so they have to be forced to do so. And this line is called the potential energy curve. We are talking now about simple case, and if we have the potential and we know the kinetic energy operator of this, we can sort of construct what we call the molecular Hamiltonian. Here is a close look. So we see here the potential energy surface of CO. If we zoom in about this global minimum of the curve, we can approximate it as harmonic oscillator. And we can use this to construct the Hamiltonian. So if we come here, we can say, okay, yeah, this little really tiny bottom is, this is tiny bottom of the curve is sort of a parabola, and this we call it harmonic oscillator. And if we look at the energies, because this is sort of a bound or a well, potential well, we see the energy are discrete. So the energy spectrum is discrete, and the energies are discrete for the following reason. Whenever you have a binding system or a potential well, the energy will be discrete. If you are outside in the continuum, so the system is not bounded, the energy will be continuous. So the discreteness in quantum mechanics does not exist forever. I mean, in every situation, only when you have a bounded system. And the lowest one, we call it the ground state, and then we have the first excited state, E1, and the second excited state, or the first overtune, and so on. We can continue the spectra until we arrive to the dissociation. And of course, each energy would correspond to a certain molecular state. Here it's a vibrational molecular state because we don't consider the rotation or the electronic transition. However, the electronic energy is this little thing. Really the lowest energy here is the electronic energy, and this distance is, we call it the electronic energy, and the levels between E0 and E1, those are the rotation. And indeed, E0 does not start from the bottom of the curve because this is called the 0-point energy. So this is in a nutshell. We get this curve, and we use this potential and express it. So we get from this curve, we get the frequency of the molecule, we can have the reduced mass, and then we can construct the potential. How this helps us? This helps us in constructing the Hamiltonian. Anything we want to describe in chemistry or in physics in general, we need either Lagrangian or Hamiltonian functions. And in chemistry, usually we use the Hamiltonian. The Hamiltonian is sort of a function that describes the total energy of the system. So it has a kinetic and the potential energy. And the operator version of it is what we use to obtain the energy spectrum of a given molecular structure. And the Hamiltonian is constructed of the kinetic energy operator and the potential energy operator. Typically, this is the more generic form of the Hamiltonian. For the we have the kinetic energy, which would consider all vibrational modes, and we have the potential energy surface. Of course, there is a lot of approximation are involved in that, like we are now talking about the Born-Oppenheimer approximation, but that will be for a more in-depth tutorial. Now we are seeing the more of a use case about the vibration only, but keep in mind that the molecular Hamiltonian is much more sophisticated. There are more terms to consider the rotation and also to consider the electronic transitions. So here is the thing. If you are considering only the vibration happens because the nuclei are moving. So we have this nuclear motion for each mode. For each vibrational mode, we have one operator, and we can sum them. And then we have a total potential which combines all of these vibrational modes. And we can have, for example, the molecular Hamiltonian for the vibration, and we need to solve it. How we get the spectra from that? We can go with two versions. The first one, we can use what we call the first quantization form. It means that we represent the Hamiltonian on a grid. So we have the kinetic energy and we have the potential. The potential, we know it. We can compute the potential on a grid. We know the RE and also the different R's. So we vary the bond lengths and we get the interaction energy at each bond length. And then we have our curve. We use this curve, put it in a diagonal matrix where the size of this matrix would be proportional with the number of points used to compute this. This is a square matrix, so and symmetric, so it's a diagonal matrix. And indeed, we can use finite elements or finite derivatives. For example, first, second order, maybe the fifth order for more accuracy, like DVR and so on. And then we have sort of -2 ones and of diagonals, and together with these two matrices, we can put them here and we diagonalize the total matrix. If we do the diagonalization, we get the energy spectra of the molecules. These are the energy eigenvalues of the Hamiltonian, and also we get the eigenvectors which correspond to the wave functions of each molecular state. Or we can go to another representation called the second quantization form. And in the second quantization form, that, of course, inspired from quantum field theory. And in that sense, you assume that you are in a vacuum and the ground state is like your vacuum state. So that's then you go from this and you go up or down, building in the vacuum. So you can build states in the vacuum. So you go by what we call ladder operators. So each operator can go up. So you go with excitation. We call it a dagger. Or you can go down in the ladder and we call it the excitation operator, and that's A. So you can construct the whole levels or the whole molecular energy levels and of course the wave functions just only using the ladder operator. So you go from n equals 0, that's ground state, to the first excited state, to the second, to the third, and so on, as much as you apply these ladder excitation operators. And of course, you can go down using the same de-excitation operator. So we have A dagger A acting on N. If you apply both, then you get the number, and this number is the number of the state. So this is the N. You get the number that's inside the quantum state. And here is the action of A dagger on N, and then you get root square of N plus 1, and then get N plus 1. So it means that you went up, and here you went down. What is this N in reality? This N is not a number. This ket N is a label for what we call a polynomial structure or a polynomial representation for the molecular state. And this is sometimes formed out of Hermite polynomials, sometimes some weighting factor and with some normalization. So you have some function here. And this function is what we have as molecular representation or the molecular Hamiltonian. I'm going to show you this type of function at the end if we have time indeed, so you can just see this for yourself. But then if you Google the harmonic oscillator or function, you are going to see the analytical representation. For the sake of simplicity, why we choose or why we can go for one representation and omit the other one. So typically each representation has its own advantage and disadvantage. For example, if you go with a grid representation, the potential is diagonal, so you don't work much. However, you might not get all the time the potential diagonally, or you might do a lot of heavy work on the kinetic energy operator. So it's good for certain use cases. A lot of packages can use it, but once you have more vibrational modes and more modes to consider, then typically we go with a second quantization because that's more natural, and of course you can deal with it using what we call basis set representation. So you can create a kernel and build in this kernel your Hamiltonian, and you can also use what we call the variational principle. I'm going to switch now to my handwriting tablet so I can show one thing. So typically, what we have here, we can have what we call a basis set, and then we have, this is the Hamiltonian, and then if you want to compute the ground state energy, so I have, this is the ladder till we go to En, and then what we try to construct is two matrices. So we have here V and T. This is the first quantization. Now, if we go to, if we don't know the ground state, or we don't know the potential or the wave function, so something missing in the Hamiltonian, then what we typically do is we use a variational principle, and the variational principle, it says that you can have the ground state, you can compute it in a sense that if you have the true energy wave function of the Hamiltonian, the ground state wave function, and then you have the Hamiltonian, of course normalized, then that gives you an upper bound on the ground state. So you can compute the ground state using something like this. And this is what we are going to use in quantum computer. Indeed, if you have the Hamiltonian in terms of the grid, you can pretty much diagonalize and have everything. But if you don't know, for example, you have your potential, but you cannot evaluate the kinetic energy operator on a grid or the potential on a grid, then the ladder operator would make sense. And then what you do is that express all of your potential in terms of these operators, and then put it here and compute this expectation value. We have seen last time that we need to compute the expectation value, and this is how we do it to get the ground state. This is called the variational principle. We can have a trial with function, we don't know what is it, and then every time we change some parameters here, and then we check, do we get the lowest energy or not? And until we get the lowest energy, then this will be the ground state energy, and the wave functions that correspond to this will be the ground state wave function. With the first quantization and the second, there is always a trade-off. If you go with the first quantization, you can always use all of grid methods. So you can use Fourier transform, you can, because now you are computing the potential on a grid. So you can do a lot of things that you can have here. However, with the second quantization is more natural to apply on a quantum computer for the following reason. The reason for that, this Hamiltonian cannot be applied directly on a quantum computer. You need a transformation, because now the quantum computer, as any physical system, so if we go to the quantum computer here, as any physical system, the quantum computer works with a qubit that has what's called spin Hamiltonian. Sometimes spin qubit Hamiltonian. There is a lot of version for it, depending on the type of the hardware. And if we have this one, that's a spin Hamiltonian here, we need just to map this to this. So that's, we need to do this mapping. So we need to make a transformation from this format to a spin Hamiltonian, which is also correspond of sort of Isaac Hamiltonian, which correspond to this spin Hamiltonian. So the second quantization is more natural to do this transformation. And if we don't, if we use the first quantization, we are gonna we have to work hard on the math to make this. But if we use the second representation, I'm backing now to the slides, then it would make sense naturally to use the quantum computer, because we can use these transformations, and there's a lot of transformations that we can use to do this mapping. So in a nutshell, the variational principle would mean that when I act with a Hamiltonian on a particular state, I get the energy of this state. So if I want to compute the ground state energy, I need to make sure that my trial wave function psi, which I denoted by psi, I update all of the parameter, and then I compute this expectation value, this average, and then when I vary all the parameters, I get a value that I cannot get less than of the, so this one will be sort of my the ground state. So I made the E0 as larger, but of course the E0 that I mentioned earlier was one coming from the variational principle. So pay attention to that. This one is the actual ground state. So what we compute is the upper limit of this ground state, this E0. So our aim is whenever we vary this trial wave function, we keep varying it until we arrive or conclude this energy corresponding to the ground state.
بس يا سلمى.
So what we have here in terms of
these things.
I'm sorry,
just
someone
muting.
is, needs to unmute.
Yeah, I think I
You're
did
not a
this
speaker,
muting.
please unmute. Please mute.
So we get here the ground state energy, and we want to compute it with the variational principle. So the variational principle is a way that to get this upper limit. It could be the true state or not, but we wanted to get the much more, or the end precise value that we can obtain by varying the parameters of this trial wave function and to compute this expectation value to get the ground state. How we do that? That's simply by multiplying two matrices, and we are going to see this in the lab shortly after the break, how this is done in reality. Okay, so now the conclusion: if we have a better trial wave function, that would yield to better approximation to the ground state. Of course, this is won't work, so I have to open it with another JavaScript. Because I don't use one, I'm just opening it now. Okay, so this animation doesn't work. So, but the main goal here is that when we go to the quantum computer, we wanted to use a variational quantum eigensolver. And what the variational quantum eigensolver would do would try to explore the ground state of a given Hamiltonian using parameterized gates. So I'm switching now to the second screen. So here is my Hamiltonian. So let's assume I have a Hamiltonian for a simple molecular system like CO. So this is my CO molecule. And this is my bond. And then I can vary this RE. So in the second quantization, the Hamiltonian takes this form. And this is my ladder operators. And what I wanted to do is to translate this into a Hamiltonian of the qubits. And typically the qubits understands what we call Ising Hamiltonian. And what Ising Hamiltonian has, it has this things. We have bunch of Pauli gates, so we can have, for example, XX plus XZ plus Y and so on. So you get what we call Pauli strings. Now, when we try this variational principle, our main goal is to find, this is my trial. The upper limit for the ground state. So I need to vary this until I get the lowest value. And to do this on a quantum computer, if I have one qubit quantum computer only, I need to use what we call parameterized circuit. And then I vary these parameters. And then I make measurement. And every time I do a measurement, and until I get the lowest state. So on a quantum computer, it's natural to do this variational principle because I have a rotational gate. And what this rotational gate does on a Bloch sphere, if I have my Bloch sphere like this, Then what I do, I have a vector that explores all of my angles here. Then I can have theta 1, theta 2, phi, and theta, of course, will go from range 0 to pi, and phi from 0 to 2 pi. And then I can explore that until I get the ground state. So I'm backing out to the original slides. So if you don't understand anything now, please feel free to visit the lab, because in the lab we are gonna dive deep into a very primitive example. So you are gonna see how this is done, and you are gonna use also IBM simulator from Qiskit and how to do so, and also use the mappers and so on. So this is like just appetizer for what we are gonna see shortly after the break. So what we do in the variational quantum eigensolver is that we use a variational principle, which is known classically. We can use it classically. However, when we do it on a quantum computer, we need to have our own Hamiltonian. We need to map it to Pauli strings. We are going to see those mappers. So it's not an advanced lecture, so that's why I'm not going to explain the mappers, but perhaps in the future versions of the school, we are going to have more time to give more about every mappers and the computational complexity, how it works, and so on, a bit of more depth view. And feel free to visit my GitHub repo and also my YouTube channel. There is a lot of more in-depth explanations for that, and also the channel of iQafé, where during the monthly series we have explained a lot of these technical tutorials. So now if we back here, we need to have our own Hamiltonian expressed in terms of Pauli strings, and our aim is to find the ground state. So we need to prepare the trial wave function. We have it, we make some sort of initial guess for the parameters, and we construct what we call ansatz. And the ansatz is just a sort of a quantum parameterized quantum circuit to prepare the trial wave function. So we make this thing, and then we optimize the parameters of the circuit. And then every time we make a measurement to see, do we get the lost energy or not? So how this is, for example, done, I'm switching now to the second screen. The quantum computer doesn't understand the molecular Hamiltonian. It only understands, or it's easy to map the Isaac Hamiltonian. So the Isaac Hamiltonian in terms of X and Pauli strings, that can be mapped easily. In the lab, we are going to take a very simple use case, which is 2z plus x, a molecular Hamiltonian that is simply has been converted into this Ising form. And what we typically do, if we have 1 qubit quantum computer, each gate of this, we map it to one of the Pauli strings. So for example, the Z could be mapped to identity, the X could map to, we can use it, for example, Ry of theta. I'm just giving an example. And what we need to do is to construct simply this. So first, we need to encode, we need to make the trial wave function. So this is a trial wave function. And to make the trial wave function, we use some parameterized gate here. This theta is random, so it's random. It has been specified by initial guess. Then we continue to encode our Hamiltonian. And then what we do is that each gate of these ones, put them here. So we get here the gate equivalent to the Z, which is, for example, in our conceptual example is I, and then X, which is R Y of pi over 2 or minus pi over 2. And then we make measurement. The measurement, we compute the expectation value. We can compute this, for example, in a certain observable. We have seen last time that we have to do that. I'm going to review it shortly. why we need to measure in observables. But then we do that. And then every time we measure our Hamiltonian, we get certain energy. Then we vary the parameters. Here we have only one parameter. So here, this is my parameterized circuit, and this is my Hamiltonian part. So what will I do? I vary the theta. And then I might get a curve like this, for example. Then theta could be pi over 4 or pi over 5 or anything. And at this value, I got the lowest energy. So this is the correct parameter or the good parameter that correspond to the ground state. The only overhead here is that I need to do this classically. So every time you update this parameter on a classical computer, so if we wanted to have this, you are sitting in your computer here, in your own laptop, and then every time you put some theta, you insert it, it goes via the cloud, and then it goes to the quantum computer somehow in the cloud on a chip, and then it back again with the result. And then you check, you make the curve in front of you. Do I get the lowest one or not? And then you keep bumping the values until you get the lowest one, the lowest theta. So that's that loop. We are talking now about very simple case. If we have very large molecular structure, then the problem you get you need more parameters. The more parameters that you have, the more accuracy you can get. And then the overhead becomes now significant. And this is why there is a lot of smart algorithms have been implemented for VQE and precisely to explore or find the good parameters that can be used to optimize. For example, you can have what we are now exploring. You can have, for example, in one qubit, you can have Ry of theta, or Z of phi, and so on. This is to prepare your trial wave function. The more parameter you have, the more accuracy you can get. And indeed, you need a very smart algorithm. There are smart algorithms that use GPT algorithms to find, or at least to predict, where this cloud of parameters will exist in the parameter space. We had a use case developed about that to find it, and the students really tried the GPT and tried also the transformers from Meta and from pretty much AI providers to really try to find the correct set of parameters. But this is also a tedious work. This is why there were also more profound smart algorithms have been put forward that we are going to see later in the school to find workaround this. So let me back to the slides again. And what we need to do is to measure an observable, and the observable here is Pauli string, so it could be X, Y, and Z. And the reason for that, we need to have something that is measurable in the lab, that has a spin up and spin down. And of course, the spin up correspond in the computational basis to kit 0, the spin down to kit 1. This is a -1. And you can do measurement, or you can have the results in a different basis like X or Y, but then you understand that you need some transformations. So that's, you need to work on with gates to either back to the Z axis, or you can do your measurement depending on the type of hardware in X or Y. This example we are going to see in the lab, so I'm not going to discuss it now. So we are going to see this in the lab. And error correction, we have discussed it last time. Indeed, when we get things for chemistry, we have to do a smart error correction. And the error correction is profound here, because when we use large number of qubits for VQE, it's not one qubit. I mean, the one qubit here is just only for simplicity. We need very large parameter space in order to do so. And if we do that, we have more errors. So we need to use smart algorithms in order to do so. I don't want to dive deep more in the theory, so I think that's enough for this first session, and perhaps we can get our hands dirty in the second part after the break. I'm gonna upload the notebook there, and after the break we are gonna see another session where we are gonna see the quantum roadmaps with Ian Plomard, and then we are gonna have the last session with Alan, Dr. Kieperl and Sharkey to discuss more about chemistry algorithms. So thanks, and yeah, looking forward for questions indeed in the chat if there is any.
Thank you, Dr. Taha. Very interesting. And the most interesting for me is that I understood. I thought I was going to miss this lecture.
Oh yeah, thanks, Dr. Ahmed. That's very nice of you
Surprisingly, I understood it. I don't know how I did that. But actually, this raises my question until others have other questions. I want to ask how quantum computing for quantum chemistry is different from quantum computing for quantum physics. Because I don't know that much about chemistry, but I think from the molecular structures from computational physics, probably this is the reason I understood. Plus, maybe knowing or having some mathematical background, so I understood what the Hamiltonian and what the Lagrangian are. I know that this may be a challenge for computing students who are not that deep into physical sciences, but it brings again the same question: how quantum computing for quantum chemistry is different from quantum computing for quantum physics.
So thanks, Dr. Ahmed. That's indeed very interesting question, and of course you are half physicist, so that's everything will be easy indeed. That's for sure. And the other half is a computer scientist, so that's indeed nice. So now for this there is not much of a difference. And this is the beauty about that. The variational algorithms and the way that the ladder operators are constructed, they are a typical mathematical rigorous way in physics and the quantum simulations in general. So they can be extrapolated into many fields. And the good thing is that what we have seen today from the variational algorithms and the variational eigensolver and this ladder operator and all of that can be easily mapped to physics, but also to finance and the machine learning. So the quantum machine learning are trying to utilize these parameterized circuits. Of course, there is a bit of more in the post-processing. There are a couple of different steps that have to be processed, like to look out for barren plateaus and all of that, where the surface is flat and we cannot find a convergence and so on. However, pretty much the skeleton of chemistry is the same. So it's the same for physics and also for finance and machine learning. So that's the beauty about that. So the quantum computing for chemistry is the same for physics. It's the only fine tune is that the expression of the Hamiltonian, the starting point, how to prepare the Hamiltonian and get the correct formalism of the Hamiltonian with the correct convention and reference frame, and then do the translation into Ising Hamiltonian or the qubit Hamiltonian, depending on the system, because the photonic is using different mathematical structures and the superconducting and so on. And then once we end up there, then pretty much we get the same workflow. We need to have a construct a quantum circuit, run the measurement, vary the parameters, make measurements, and so on. And the clever way is how to shrink this circuit and do a clever ways of and to not end up with very huge lengthy quantum circuits, to shorten it so it become feasible and reduce the errors in the runs.
Very interesting. Thank you very much.
Yeah, thanks very much, Dr.
I don't see hands or questions in the chat, so if we don't have questions, I think we can conclude the session to take the whole half hour of. We have a question from Alain Chanté.
Actually, I wanted to add on top of what.
Alain, your voice is far. Your voice is far. We hear you very. Yeah.
So I just wanted to complete the answer from Taha. I'm aware that there is a beautiful mapping between finance and chemistry. The Black-Scholes formula can be mapped to quantum chemistry, and conversely, which means that by this mapping and leveraging the knowledge of quantum chemistry, it's possible to actually solve with a quantum computer, problems related to finance. So this is the beauty, and this is also what makes it possible to do analog simulations. We're talking about digital quantum computing, but analog quantum computing exists because the underlying mathematical model can be the same between quantum chemistry problem and some other problem. So this is one very strong advantage of quantum computing. So that's what I wanted to share.
And thanks, Salah, for pointing out to this, because tomorrow we are going to have a session about the quantum finances. So hopefully you are there to see what Alan has pointed out, that how Black-Scholes is emulating the behavior of Schrödinger equation and that kind of nice, beautiful symmetry. And this is actually what makes people coming from chemistry or physics can work in banks comfortably, because just can leverage the same mathematical knowledge.
Yeah, and I would add that the Monte Carlo methods were actually initially invented by quantum chemists, and then later the folks from finance used it very effectively. But the Monte Carlo approach has been used in quantum chemistry for, I don't know, 40 years or so. So it's interesting. There is this crossbreeding between apparently completely different domains, but there are the underlying mathematical model can be the same. So that's also good news for people looking for a changing job. If you have expertise in finance, you could be useful in quantum chemistry, maybe, and conversely.
Excellent. Well, thank you very much for the insight. Do we have any? Let me look at the chat before we. Where can one dig deeper in Hamiltonian? Well, the deepest is Google. You will get millions of sources on Hamiltonians and Lagrangian. Perhaps it depends on the level of mathematics. If it requires something else before the Hamiltonian, it will keep taking you one step at a time until you reach what you want. There are no limits to what you can learn on the internet nowadays. Well, maybe Dr. Taha or our friends, if you have a better answer, maybe you can provide it.
Yeah, I think thanks, Dr. Ahmed. I think, that's a better way, but we are going to discuss it in the lab. So perhaps in the lab, we are going to discuss more about the Hamiltonians and the construction. And indeed, if you like to explore for more larger systems that are not covered before, it's a bit tricky to use AI, because AI want to understand the convention of active space, passive space, and passive rotations, and so on. So you need really to learn about that. However, there is a lot of nice databases I can guide you through, which contains pretty much of Hamiltonians for small systems, and sometimes for large systems whenever there is a work on that. I can also show you the paper I worked on my PhD. We did it as a review article where we cover everything for the CO2 plus what we have done to show how this systematically is developed. So you can also get insights how these Hamiltonians are constructed, and you can use the same method for other use cases and the other molecular structure as well.
But if I understood right, I think Mina Wahib, who asked the question, I think was not looking really for deeper Hamiltonian, but maybe was looking for basic understanding of the Hamiltonian to know more or develop better understanding of the Hamiltonian. I think if this is the case, I would advise that you dig for it on Google during this half hour of break. If it is about real deep work with the Hamiltonian, then the advice of Dr. Taha would be the best for you next. Okay, some are asking Dr. Taha to share that paper.
Yeah, we'll share it shortly in the chat. Yeah.
Okay. All right. I think for people not to miss their break, we can start the break now. And we reconvene at 8:05 to take the whole 30 minutes. Thank you very much all.
Yeah, thanks a lot, and yeah, see you in a bit.